Hello, I'm making this video after school, not in front of the class, so I might go a little fast. If it's going too fast, just pause it. This is after having taught this today to block 1A. It's probably new for all of you. Most of what we did in this unit, solving inequalities, was not new. It seemed like review. But this is new. Compound inequality means two inequalities joined by the word and or the word or. Examples would be x is greater than 1 or x is less than 0. X is greater than 2 and x is greater than negative 2. These are statements altogether that are true or false based on what is understood about the words and or, and not purely in a math context. In fact, it's more of a logical context than purely what you might call math. Maybe logic is math. For example, if I say, or if you say, I'm going home and I'm going to 7-Eleven, I use the word and to join those two statements. If I go home, but I don't go to 7-Eleven, is the statement that I made true? And the answer is no. I said I was going to both. I didn't go to both. I just went to one, so I have to say that that is a false statement. Now, if I go home and I go to 7-Eleven, then it's a true statement. I said I was going to go home and I was going to go to 7-Eleven, and I did, and that's a true statement. If I make a statement, a compound statement, I am going home or I'm going to go to 7-Eleven. If I go home but I don't go to 7-Eleven, is it true? And the answer is yes. I didn't say I was going to both. I said I was going to go to one or the other. And I went home. So that's a true statement. Now, you might ask the question, what if I go home and I go to 7-Eleven? Is an or still true if both parts are true? And the answer is yes. As long as at least one part is true, then the overall or compound statement is true. So for a compound and to be true, both parts have to be true. For a compound or inequality to be true, just one part has to be true, but it's okay if both parts are true. So let's look and see how, when we graph compound inequalities, that they come together. Here I have a compound statement, x is less than negative 1, or x is greater than 1. Now, I've graphed both of those on the bottom two number lines, and I'm going to use the top number line to graph the compound inequality. Remember, for the compound inequality to be true, just one part, one of these two statements has to be true, one of these two inequalities. So since on the middle number line it's highlighted from negative 1 to the left, then it has to be highlighted from negative 1 to the left on the compound inequality. And since the lower number line is highlighted to the right of 1, then it also has to be highlighted to the right of 1. So the compound inequality is both shaded areas all together. And the way you say that is, again, with the compound inequality, x is less than negative 1, connected by the word or to x is greater than 1. It wouldn't be quite the same if you didn't include the word or. Now, if I say x is less than negative 1 and x is greater than 1, I'm starting with the same two inequalities that I used on the last slide, but this time I'm connecting them with the word and. And I know that in order for the compound inequality to be true, both of the inequalities have to be true. So really what we're looking at on the number line is, do either one of these two, the middle number line or the lower number line, do they overlap? Are they shading in the same part of the number line? Because that's what it would look like if they were both true. And the answer is no. There's nowhere from negative side of the number line to the positive side of the number line where you can say that both of the graphs below are highlighted. Just one is highlighted to the left of -1. Neither one of them is highlighted in between -1 and 1, and just the one on the bottom is highlighted to the right. So you would have to say, if you tie those two together with a compound, with an and, then you'd have to say no solution. Okay, now let's try x is greater than -1 and x is less than 1. So a graph that x is greater than -1 in the middle number line, right? Open circle on -1, shaded to the right, right? The x is less than 1 is on the bottom number line. There's open circle on 1, shaded to the left. Now the compound inequality will shade in here. The question is where to shade. Okay, we should shade the compound inequality everywhere where both the bottom two number lines are shaded. And the bottom two number lines are both shaded from -1 to 1. Now, are they both shaded at x equals -1? And the answer is no. This one is actually open circle, so it would not be correct to say that they're both include -1. So the top graph cannot have a closed circle on -1. And for the same reason, right, we have to say open circle on +1. But in between -1 and 1, both of these are shaded. So that means the compound and would include that part of the number line. All right, now compound or. Same two inequalities, x greater than -1, x less than 1. But we're tying them together with an or. Now, in order to shade the top, I only need one of the bottom two number lines to have been shaded. Okay, so to the left of -1, right, the bottom number line is shaded. At -1, the bottom number line is shaded. In between -1 and 1, they're both shaded. At 1, the middle number line is shaded. And to the right of 1, the middle number line is shaded. So basically, everywhere on the number line, one or the other is included. So that means it has to be included here. It's the whole number line. The solution to the compound inequality is all real numbers. Okay, one more, or actually two more. This is an and. So we're looking for where do these two graphs overlap. X is greater than -1 and x is greater than 1. And just looking at the two graphs, it would appear that they're both shaded to the right of x equals 1. So I would have to come up here and shade to the right of 1. That is the graph of the compound inequality, just the shading that goes to the right of 1. And in fact, the compound inequality, the solution is x is greater than 1. Right? You don't even need the x greater than -1. Now that would change if I connected those two with an or. Right? Now, in order to be included on the compound inequality, it just has to be included on one of these two. So that'll actually start here and go to the right. And again, you could say that the whole compound inequality boils down to that. X is greater than -1. Okay, so that's just all kind of set up so that we can start doing some of the examples in the book, which are going to be like your homework problems in the book. Translate the verbal phrase into an inequality, then graph it. All real numbers that are less than 0 or greater than or equal to 2. Okay, let's see. All real numbers. The all real numbers part is going to be represented by an x. We are interested in those values that are less than 0. X is less than 0. Or x is greater than or equal to 2. So there's a compound inequality. It says graph it. 0 and 2. Right? Because it's not or equal to, I'm going to use an open circle on 0. And since it's to the less than, which means to the left on a number line, I'm going to shade to the left. X greater than or equal to 2. Okay, it includes 2 because of that bar. So let me shade that in, color in the circle, and then shade to the right. Right? Because greater than on the number line means to the right. Okay, translate the verbal phrase into an inequality. Okay, this is a particular kind of inequality, and again, this is part of what we're doing today that is going to be new to you. Asking my Block 1A kids, it seems like you have not had this before, and what I see in the classes that I teach above this level, that there's a lot of kids that don't deal with this very well. And I never knew whether it started before Algebra 1 or does it start in Algebra 1. And from what I thought I learned today, I think it starts in Algebra 1. So please try to learn about this new thing, which is called a three-part inequality. Right? If I say all real numbers that are greater than -2 and less than 3, let me put the -2, let me put these on a number line first. Okay, -2 is here, 3 is here. If we're looking for all the real numbers, which again is our x, that are greater than -2, that would say that they have to be to the right of 2. And they're less than 3, that would say that they are to the left of 3. And the fact that we're using an and means that we're only interested in the part of the number line where both of those are true. And where is that? That is true in between -2 and 3. So the way that we would show that, since the x is in between -2 and 3, I'm going to put the x in between the two, and then I would use the less than inequality symbols, because on a number line, less than means to the left. -2 is less than to the left of x, or the shading, and that shading is less than to the left of 3. So this here is called a three-part inequality. And three-part inequalities come up. They'll come up in the future, provided you stay on a reasonable math path. You're going to have to know about three-part inequalities. Now, you could look in the book. The book will show you that you could say, I could say x is greater than -2, and I could use the word and I could say x is less than 3. And in a sense, it does say the same thing, as long as I use that word and. But we do need to know what a three-part inequality is. You're going to see it. You're going to see it over and over again. And it just can't be so complicated. It just means that x is in between the number on the left and the number on the right. Notice that these symbols, less than and less than, they're pointing in the same direction. They have to. So this will be your U-try. You can do this. I'm gonna go ahead and do it almost right away, so please pause the video if you're going to try to do it before you see what I do. And then when you're done, hit play. Translate the verbal phrase into an inequality, then graph all the real numbers that are less than -1 or greater than or equal to 4. Right? This is our x, all the real numbers. All the real numbers that are less than -1 or all the real numbers that are greater than or equal to 4. Right? That's what that phrase says. And if I put it on a number line, here's my -1, here's my 4. Open circle on -1, shade to the left, less than means to the left. Close circle on 4, shade to the right, greater means to the right. Now the fact that it is a or compound inequality means the graph includes both of those areas. Okay, translate the verbal phrase into an inequality. All real numbers that are greater than or equal to -3 and less than 5. So again, you can write it like x is is greater than or equal to -3 and x is less than 5. But when I put it on a number line, greater than or equal to -3 means closed circle, shaded to the right. Less than 5 means open circle, shaded to the left. But we know for a compound inequality that the only shaded that's part of the solution is where these two graphs overlapped, and that would be here. So if you're doing this on a quiz or a test, you can't just draw these two arrows and then walk away from it. You gotta show me you understand that it means only that area in between -3 and 5. And really, better than writing two inequalities and using the word and is just show it as a three-part inequality. -3 is less than x is less than 5. So three-part inequalities are implied and compound inequalities. And you should use a three-part inequality when they are appropriate. Please don't just keep trying to write it as two different inequalities. It's going to lead to more mistakes. And it's not like you can just do it a few times and be sure that after a while they'll just go away and you won't have to know them. Actually, that is not true. They're not going away. You will have to get comfortable with a three-part inequality. This is example 2 in the textbook, this section, 6.4. A crane sits on top of a camera car and faces toward the front. The crane's maximum height and minimum height above the ground are shown. It looks like the minimum is 4. And the maximum is 18. Looks like this is a truck. It has the crane on top, and at the end of the crane is a camera, so I guess it's going to be filming or taking pictures. There's a certain range of motion that it's got. It can go down as low as 4 and as high as 18. So write and graph a compound inequality that describes the possible heights of the crane. Okay, can the crane be less than 4 feet high? No, because it looks like it only goes down as low as 4 feet. Can it be higher than 18? No. It can be between 4 feet and 18 feet. Whenever I use that word between, and I use it a lot when I'm doing these inequalities, you should be thinking compound inequality. Right? Here's our three-part inequality. Here's our three-part inequality. 4 is less than height, I'll call it h, is less than 18. Now, there could be a question of, do we make these or equal to's, or do we leave them as not or equal to? Does it look like 4 feet high is an option? Looking at the picture, I think it is. So I think I would do this. I think I would make it or equal to or equal to. And if I had to graph it, and I do, it would look like this. 4 on the left, 18 on the right, close circle on both because I added that bar to make them more equals, shade in between. So all the heights in between 4 and 18 are reasonable for the camera. All right, now when we solve, now we're going to get into solving compound inequalities. And when you solve a compound and, or sorry, I shouldn't even say that. When you solve a three-part inequality, what you have to remember is, up till now, we've always isolated a variable on one side of a two-part equation or inequality. And we did that by doing operations to both parts, to both sides. But with a three-part inequality, we're going to isolate the variable in the middle part of the three parts. And we're going to do it by doing operations to all three parts. So let me go to the next. That's the same problem. So again, if I need to isolate the x is here. It's in the middle part of the three-part inequality. I have to say to myself, what's with the x that needs to be moved so that the x is isolated by itself? And the answer is 5. Right? Well, how am I going to cancel a plus 5 in that's with the x? Well, I'm going to subtract 5. So if I subtract 5 here, because there's three parts to this inequality, I have to subtract 5 here, and I have to subtract 5 here. Whatever you do to the middle part, do to the other two parts. Negative 3 is less than x is less than 4. Right? Graph your solution. Negative 3 is less than 4, so I'm going to put them in this order. I am going to use open circle on both because they are open circle, and I will shade in between negative 3 and 4. So again, solve three-part inequalities by isolating the variable in the middle by doing operations to all three parts. And I think my point here was just to show if you do it with two different inequalities, right, you're going to need to solve them both first. Subtract 5, subtract 5. Negative 3 is less than x. Subtract 5, subtract 5. X is less than 4. Remember that it's not 100% correct unless you use the word and in between those two. And the graph I'll draw it in two parts. First, I'm going to draw negative 3 is less than x, which means negative 3 is to the left of x. Then I'm going to draw x is less than 4, so that goes to the left of 4. And then I've got to say, well, since this is a compound and, I need to shade in between negative 3 and 4. So, and if it's me, even if I've done it with two different inequalities at that point, I'm going to say negative 3 is less than x is less than 4, which is just describing what is in front of me. Okay, so here's a couple for you to try. So go ahead and do that. Hit pause if you want to do it. And not have me telling you the answer before you're done. Okay, so hit pause now and hit play when you're done. So I'm going to move pretty quickly through this. Right, that's the first one. If you did the first one and you just checked it, you might want to hit pause again. And I'm going to go ahead and do this. Okay, so go ahead and hit pause. At this inequality, it's actually going to take 2 steps. So it's a 2-step, 3-part inequality. Minus 4, minus 4, minus 4. 6 is less than or equal to 2y is less than or equal to 20. Divide by 2, divide by 2, divide by 2. Remember, if I do it to the middle part to isolate the variable, I got to do it to all 3 parts. 3 is less than or equal to y is less than or equal to 10. So y is in between 3 on the left and 10 on the right. And they were both or equal to, so I use closed circles on 3 and closed circle on 10, and now I'm shading it in. So you might ask yourself a question about, do these inequality symbols, when you do a 3-part inequality, are they always less than? And the answer is no, they're not. And I'm pretty sure the next question we're going to see that. But here's one thing they are always. They always go in the same direction. Right? So 10 is less than 2y plus 4 is less than 24. Right? It's never going to be less than here and greater than here, or vice versa. Okay? These have to be pointing in the same direction. Okay, so here's the one I was telling you about. And you might notice right away what's going to be different about this one, but I'll just go ahead and go through the steps of solving. So to isolate the variable, first I'm going to add 1, right? But if I add 1 to the middle, I add 1 to the left, and I add 1 to the right. And now I have negative 6 is less than negative z is less than 4. Okay, is the variable isolated? No, it's not isolated because it has a negative in front of it. So how do we get rid of a negative? So that we've solved for the variable? The right answer, the best answer, is we're going to multiply by negative 1. If you said divide by negative 1, it's still a good answer. It'll still work. But remember, we had a multiplication property of negative 1 for a reason, because that's how you can flip the signs of things. So I'm going to show this on a new line, because at the moment I show myself multiplying by a negative, I've got to flip the direction of the inequality signs. So this is negative 6. I didn't mean to say that. Sorry. This is going to be negative 1 times negative 6 is less than, oops, I am making mistakes, getting late, is greater than, right? At the point I multiply by negative, I got to flip these. Negative 1 times negative z is greater than negative 1 times 4. Simplify. Negative 1 times negative 6 is 6. Negative 1 times negative z is z. And negative 1 times 4 is negative 4. Okay, make sure that this number on the left now is actually, it makes sense to say if 6 is greater than z and z is greater than negative 4, it should be true that 6 is greater than negative 4. That's called transitive property. And in fact it is. Okay, if you make mistakes in here, then that might be someplace you see it. Like if I didn't flip these signs, it would be telling me that 6 is less than negative 4, and that's not right. Okay, but this is correct. Sorry for my wiggly line, but I think we get the point. Okay, what number goes on the left? It's not 6, right? 6 is on the left, but it's greater than negative 4. So I put negative 4 on the left and 6 on the right. Okay, both of these are not or equal to, so I use open circle, and I shade in between. Okay, now everything we've seen up to now was always a three-part inequality, which means we always had the same expression involved. But it won't always be like that. It could be like this too, right? 2x plus 3 is greater than 9, and 3x minus 6 is less than 12. This we can't solve as a three-part inequality. We just need to solve both of these, put their graphs on a number line, and look for the overlap, right? Minus 3, minus 3. 2x is greater than 6. Divide by 2. Divide by 2. X is greater than 3. Okay. Add 6. Add 6. 3x is less than 18. Divide by 3. Divide by 3. X is less than 6. And again, those are tied together with and. So here's my 3 on the left and my 6 on the right. Both of them are open circle. X greater than 3 means open circle on 3, shade to the right. X less than 6 means open circle on 6, shade to the left. Okay, now I've got to indicate where's the solution of this compound inequality? Is it the whole number line? And the answer is no. Because it's an and, it's only the part of the graph where both of those graphs overlap. And they overlap between 3 and 6. So you can add it in. 3 is less than x is less than 6. That certainly describes the area of the graph, which is shaded. Okay, now we're going to solve not quite the same problem. All the expressions are the same, but it's also an or. So let's see. Subtract 3, subtract 3. 2x is less than 6. Divide 2, divide 2. X is less than 3. Add 6, add 6. 3x is greater than 18. Divide 3, divide 3. X is greater than 6. I know I'm going kind of fast, but again, you can pause at any time if you're taking notes as you go. And again, we got to use the word or to tie those two together. And the graph will look like x less than 3, x greater than 6. Open circle on 3, shade to the left. Open circle on 6, shade to the right. Since it's an or, we only need one part of that, one of those inequalities to be satisfied so that we include it in the graph of the compound inequality. So basically it just means we're going to create the union of those two sets. That's all of this together is our answer. Okay, now here's your you try. And if you want to hit a pause now, I'm going to go ahead and do this. This is one problem, right? It's two different inequalities, but it's one problem because they are connected with the word or. Okay, go ahead and pause. Okay, minus 1, minus 1. 4c is less than or equal to 4. Sorry, 4c is less than or equal to negative 4. Divide 4. Divide 4. Should I have flipped the less than or equal to? I see a negative 4 there. Should I have flipped it? The answer is no, right? It's not just because there is a negative 4 in the problem. It's because you are dividing by a negative. That's when you flip. But we're not dividing by a negative. We're dividing by a positive. So don't flip the symbol. Right, c is less than or equal to negative 1. Add 3. Add 3. 5c is greater than 20. Divide 5. Divide 5. c is greater than 4. And again, I'm going to bring down my or graph. -1, and 4. Close circle on -1, shade to the left. Close circle on 4, shade to the right. And because it's an OR, both areas are included in the solution. Okay, find the errors. That means we're at the end. Find the errors. If you want to pause for a second before I give away the secret, then go ahead and do that. Find the errors. You know, the first thing you might be drawn to is you see that there's a -2x, and you're thinking, ooh, when they divide by -2, I'll bet you they're going to forget to flip those signs. But they didn't, right? They actually, the less than's became greater thans, so that's good. So it wasn't that. What was it? Well, let's see, they isolated the variable in the middle first by subtracting 3. And it looks like they've lost the 3 in the middle part. They subtracted 9 minus 3 on the right, but they didn't do 4 minus 3 on the left, right? They should have done that, right? The result of that step right there, it should have looked like 1 is less than -2x is less than 6. So there's their mistake. And I could finish this just to say we did. That'll be 1 over -2 greater than -2x over -2 is greater than 6 over -2. So -1/2 is greater than x is greater than -3. Does that seem right? The only thing I'd be looking at, make sure that -1/2 is actually greater than -3. And it is. And both of your inequality symbols are pointing in the same direction, so I think you're in good shape. Okay, look at the one on the right. Pause if you want right now. What did they do wrong here? It looks like they had a compound OR, which they solved. On the left, it looks like they added 2, and they did that good. They did that well, sorry. On the one on the right, they subtracted 8, and they did that correctly. So what did they do wrong? Let's see. X greater than 7, that would have been open circle on 7, shade to the right. They shaded to the left. X less than -10 should have been open circle on -10, shade to the left. So their mistake was they shaded the wrong direction. Okay. And that should do it. So again, this might have been a new lesson for you today. Compound inequalities. And it is the last lesson of this unit. We will review next class and test the class after that. Homework is right there.